Shot effect. Electrons of charge E are emitted at random from the hot filament of a vacuum tube. To a good approximation, the emission of any one electron does not affect the likelihood of emission of any other electron. So this sentence is talking about statistical independence of two events. Okay, so let me note here statistically independent events. Consider any small time interval delta t, then there is some probability p that an electron will be emitted from the filament during this time interval. So p is the probability that an electron will be emitted from the filament during this time interval. Then therefore q, which is 1 minus p, that an electron will not be emitted. Since delta t is very small, the probability p of emission during this time interval is very small. P is much less than 1. And the probability that more than one electron will be emitted during the time interval delta t is negligible. So we can only emit one electron. So only one electron can be emitted. Okay, consider any time t which is much larger than delta t. During this time there are then capital N equals t over delta t possible time intervals delta t during which an electron can be emitted. The total charge emitted in time t can then be written as the sum of all the charges emitted, where q sub I denotes the charge which is emitted during the ith interval delta t. Thus q sub I is equal to E if an electron is emitted, and q sub I is equal to 0 if it is not. So let's see what this is saying. So if an electron is emitted, q sub I has a value E, and the probability of emission of a single electron was P. If an electron is not emitted, q sub I is equal to 0. The probability of not emitting is q, and we also know that P is much less than 1. Okay, what is the mean charge q bar? So we need to calculate total charge q bar emitted from the filament during the time t. What is the dispersion of the charge delta q square bar emitted from the filament during the time t? Make use of the fact that p is much less than 1 to simplify the answer to this question. The current emitted during the time t is given by q over t. Okay, so current is q divided by t, the total charge emitted divided by the total time interval t. Relate thus the dispersion of the current to the mean current to show that delta I square bar is equal to E over T I bar. The fact that the current measured during any interval t exhibits fluctuations which become more pronounced the shorter the time interval, i.e. the fewer the total number of individual electrons involved in the emission process, is known as the shot effect. So let's see what shot effect is. For small capital N, so we have a short time interval t, the fewer the total number of individual electrons involved in the emission process, the current is going to exhibit significant fluctuations. So the standard deviation will be significant. This is shot effect. Okay. Calculate the standard deviation of the current. If the mean current is 1 microampere and measuring time is 1 second, so now finally we need a numerical result. Okay, so let's talk about part A. First of all, the total charge emitted Q is the sum over I from 1 to capital N, all time intervals, and I'm looking at the charge emitted at each interval, Q sub I. And if I look at Q bar, the average value of the total charge emitted, this will be I equals 1 to capital N Qi bar, and we have Q1 bar equals Q2 bar equals Qn bar equals Q bar. Since the electron emission processes are statistically independent. So we have identical processes that are statistically independent. So we can write basically then the total charge emitted Q bar will be equal to sum I equals 1 to capital N Q bar, which is just N times Q bar. So what is Q bar? Q bar, so Q can have two values, E with probability P and 0 with probability Q. So I find that Q bar is equal to E times P. So this is looking very similar to the previous two problems, so it would probably be handy to have Q square bar as well. So Q square bar would be E square with probability P, 0 square with probability Q. So Q square bar, on the other hand, is E square P. So we should keep these answers here. And if you want to look at delta Q square bar, the dispersion, it is Q square bar minus Q bar square. So it's E square P minus E square P square. So this would be E square P 1 minus P. And so I would find that the dispersion of Q, lowercase q, would be approximately E square P, since P is much less than 1. So let's keep these in mind. We have Q bar is equal to EP, Q square bar is equal to E square P. The dispersion or variance of delta Q of Q is E square P, which is true for P much less than 1. Now going back to part A of this problem, since I have Q bar is equal to capital N lowercase q bar, so I would find that this is capital N EP, and then capital N was basically T divided by delta T, so that is mentioned here. Capital N is the total time divided by the time intervals delta T. So I can substitute here T divided by delta T EP. So this is going to be the average total charge emitted in time interval T. Total time interval T. Now in part B of the problem, I want to know the dispersion of the total charge emitted in this time interval. Okay, so dispersion delta Q square bar, this we know is Q square bar minus Q bar square. So I already know what Q bar is. I don't know what is Q square bar. So Q square is, using the definition basically that the total charge is the sum of all the charges emitted in each interval. This is going to be sum I equals 1 to capital N Qi multiplied by sum j equals 1 to capital N Qj, which can be written as we did previously, sum I equals 1 to N Qi squared plus sum I and j from 1 to capital N, but I is not equal to j, qi qj. So I'm doing this rather automatically here because we have done it several times. So this tells us that q square bar is equal to capital N times q square bar. So if you take the mean value here, and then we have capital N minus 1 q bar squared. So if you look at um, q square bar is capital N q square bar, n squared q bar squared minus capital N q bar squared. So I find that q square bar minus q bar squared would be equal to capital N q square bar plus capital N squared q bar squared minus n q bar squared minus q bar squared, which is basically here, this is the same thing as capital N times q bar, right? So the same result here. So this is n squared q bar squared. So these two would cancel, and I would find the familiar result that delta q square bar is equal to capital N times delta q lowercase q square bar. So all I have to do is to look at the result for the dispersion of lowercase q, which is e square p. So this would be capital N approximately capital N e square p, or I can write the dispersion of capital Q as approximately, because I'm using p much less than 1 result here, t divided by delta t e square p. Now notice that this q bar was t over delta t ep, so this is just basically e multiplied by q bar. So this is going to become handy in part C. So let's take a look at part C. Now I'm going to calculate the mean current and the dispersion of the current. So what is the mean current here, given that current is defined as total charge emitted in the time interval t. So if you look at the mean value of the current, it would be q bar divided by t. On the other hand, if I look at the dispersion of the current, delta I square bar, this would be I square bar minus I bar squared. So for I square, I can write this as q square over t square. So I square bar will become q square bar divided by t squared. And then for I bar, I have q over t. So delta I square bar, the dispersion of the current, would be q square bar over t squared minus q bar squared over t squared. So this would be equal to 1 over t squared times delta q square bar, the dispersion of the total charge q. So I find that since the dispersion of the total charge q was E times q bar, that was shown in part B, so this is equal to E times q bar divided by t squared. So I find that the dispersion of the current is E over t multiplied by q bar over t, which is the mean current. So I can write this as delta I square bar is E over T I bar. So I was asked to show that this is the case in part C, and I see that indeed that is the case. Um, delta I square bar is E over T I bar. Now in part D, I'm going to calculate the standard deviation of the current. The standard deviation of the current will be root mean square root of the variance of the current, delta I square bar. So this would be equal to square root E over T times I bar. Now, in the problem statement, it is given that the mean current is 1 microampere and the measuring time is 1 second. So T is 1 second. The mean current is 1 times 10 to minus 6 ampere. That's 1 microampere. So what is the standard deviation in the current in this case? It is going to be square root of the electron charge, 1.6 10 to minus 19 coulombs. The current, 1 times 10 to minus 6 amps, 1 microamps, divided by 1 second. So we find that this is going to give us approximately 4 times 10 to minus 13 amps, or 0.4 picoamps. So that will be the amount of fluctuation amplitude in current, 0.4 picoamps. And remember, the problem basically states that the shot effect is called the increasing fluctuation amplitude in the current in the decreasing time interval. So you can see that explicitly here as the time interval t decreases, since delta tilde I is proportional to 1 over square root of t, you will see that the fluctuation amplitude, as this decreases, fluctuation amplitude increases, so the fluctuations will become more significant, which is called the shot effect. Okay, so let's review what we said. We're talking about electron emission from a hot filament in a vacuum tube. The emission processes are statistically independent. The probability that an electron gets emitted in a time interval delta t is p, and that probability is rather small, and the probability of emission of more than one electron in this time interval is negligible. So this time interval is chosen small enough. In a total time t over delta t possible time intervals exist in which we're counting the number of emissions, and the total charge emitted in the total time t will be the number, the electron charge emitted in each time interval. The sum of all the electron charges emitted in each time interval, so it would be Q1 plus Q2 all the way up to Q sub capital N. And an electron gets emitted, the charge contribution is E with probability P. Electron does not get emitted, the charge contribution is none with probability Q. The current emitted during the time interval t is the total charge emitted divided by time t, and we want to know what is the mean total charge emitted, dispersion of total charge, the dispersion of the current and mean current relationship, and also the amplitude of the current fluctuation, that is standard deviation of the current, for a mean current of 1 microampere and 1 second measurement time. So we have noted that Q is the sum of all the charges, and the mean value of the charge is E times P plus 0 times Q is EP. Q square mean value is E square P plus 0 square Q, which is E square P. Therefore, we can calculate the dispersion of lowercase q, which is q square bar minus q bar square. So it's E square P minus E square P square. Since 1 minus P is almost 1, because P is much less than 1, it's approximately E square P. And the mean total charge emitted is sum of the charges emitted, I equals 1 to capital N, and for each one the mean value is the same, q bar, which is EP, so capital N times EP, which is T over delta T times EP. And for the dispersion of charge, I have shown this explicitly once again here, but you can also recall it from the previous two problems, that the dispersion will be given by capital N times dispersion of lowercase q. So this is, which is something I calculated in part A, E square P, so capital N E square P, which is T over delta T E square P, and I note that it is actually the electron charge times the mean charge q bar. And the total current emitted is total charge emitted per time in the total time t. So the mean current emitted is q bar over t. And for the I square bar, I have I square equals q square over t square. So when I take the average, it's q square bar divided by t square. So q square bar divided by t square minus I bar square, which is so this is basically, I'm writing here delta I square bar as I square bar minus I bar squared. I find that it is 1 over t squared times the dispersion of q. The dispersion of q was E times q bar, so it is E times q bar over t squared, and q bar over t is the mean current, so I find that the dispersion of the current is E over t times the mean current. If I just take a square root of this value, I get the standard deviation, which is square root E over t I bar, where I realize that the standard deviation varies as 1 over square root t and the measurement time. So the longer the measurement time, the less will be the fluctuation amplitude in the current, or the less the measurement time, the more fluctuations in current I will observe. So for 1 microampere 1 second values, I find 0.4 picoamps of standard deviation in the